Hello everyone, my name is Jemima, I'm from the University of Reading, and I'm going to talk about how we can use reconditioning methods to include correlated observation error, so kind of following on a bit from Craig's question. So we just had a very nice talk from Alison, motivating why we might want to include correlated observations in a data assimilation framework, but we've seen that we have these methods that we can use to estimate correlated observation errors, and Alison also introduced the de Rosier et al. Diagnostic, which I'm going to kind of be talking about today. One problem is that when we diagnose these correlation matrices, we get matrices that are really ill-conditioned, and when we try and use them directly, we don't get convergence of our data assimilation systems. We also have other problems that they're not symmetric and they're not positive definite, so they're not actually covariance matrices at all. So in practice, what this means is that we treat them to make them symmetric and positive definite. And because we're already kind of fiddling with them a bit, this maybe means that it's not such a big problem to also go playing around with the eigenvalues. And if it means we can include some correlation information in our data assimilation systems, that's probably positive. Okay, so what is reconditioning? It's any method that we can use to improve the conditioning of any matrix but preserve the structure. This is very broad, but basically, that's because it's very application dependent. So in this example of the data assimilation problem, we have a covariance matrix in the beginning. We'd like to have a covariance matrix at the end. So that's kind of the structure we're interested in preserving. But in other applications, you might want to preserve different types of structure. So a lot of methods that can be used for data assimilation are kind of methods that have been used for other things that also have the effect of doing this reconditioning. So some things include thresholding, which is where we throw away anything below a certain value, tapering or localization, which is where we put more weight on stuff that's closer together in space. That can have an effect on the condition number, and any other kind of general regularization or optimization method. But I'm not going to be talking about any of these today. I'm going to be looking on two methods that are actually used at weather prediction centers, and both of these work by altering the eigenvalues of the matrix. So just as a quick recap, I'm using the definition of the condition number where we've got eigenvalues, so lambda 1 is the maximum, lambda p is the minimum, and the condition number is just going to be the ratio. And we can do this because we're assuming everything is symmetric, positive, definite. If it's not, then we can take the condition number to be infinitely large, but basically the methods I show you today will ensure that we have a strictly positive definite. So this is what we're going to be talking about today. And the reason we care about the condition number of the matrix is because it's related to convergence properties. Okay, I'm going to be talking about two different methods, but before I describe them in detail and talk about some mathematical theory, I think it helps to have a picture. So I've made this made-up example where I have this black line, which is my original spectrum of eigenvalues. So here I have quite a small maximum eigenvalue, but I have lots of very small eigenvalues that are going to be causing problems with the condition number. I, a user, know that my system can't cope with this. So the way both of my methods work is I pick a target condition number, kappa max, that I think I can deal with. That could be 100, 1,000, your favorite number, anything you think is reasonable for your system. And then I have these two methods that give me back a matrix that has some of the same structure, but will have the condition number that I want at the end. So the first method, which is always going to be in red, is this ridge regression method. And the way this works is we're increasing all the eigenvalues by exactly the same amount here. The second method, which is called the minimum eigenvalue method, we kind of keep this top part of the spectrum the same as what our original spectrum was, and we have this threshold below which all the eigenvalues are the same. So I'm going to be applying this method to the covariance matrix, and I'm interested in what happens to the standard deviations and the correlations. Okay, slightly more formal definitions now. So the ridge regression method is the same as adding a scalar multiple of the identity to the original correlation matrix R. This is kind of quite a standard way of regularizing a system, and it's used quite a lot in optimization. And the way that we choose the scalar, which is delta, is basically it's dependent on this maximum eigenvalue, this minimum eigenvalue, and my target condition number. And then I just add a scalar multiple of the identity. It's really cheap to implement. It's similar to stuff that's been studied in optimization, which means we can develop some theory. And this is what's used at the Met Office at the moment. Okay, so we're interested in what happens to the standard deviations and the correlations, because that would be good to know. So using the mathematical definition here, we see that the updated standard deviation is equivalent to the square root of the original variance plus this delta term. So what this means is if we think about the variances, we're increasing the variances by a constant amount, and that's our delta that we kind of designed at the beginning, which is good. With the correlations, we can also say something theoretically. So we, if we take the absolute value of the correlations, they reduce when we apply this method of reconditioning. So we're shrinking all our correlations close to 0, apart from the diagonal, which stays equal to 1. So this kind of makes sense. We're taking weight off of the off-diagonal and putting it on the diagonal. OK, the second method, the minimum eigenvalue method, we have this threshold t, below which everything is set equal to that threshold. And again, the threshold is chosen so that we get the target condition number kappa max. OK, so we keep our maximum eigenvalue fixed. We find our threshold. We apply our rule of is it larger, it stays the same. Is it smaller, it's the threshold. And a final definition, gamma is going to be basically the difference between our threshold and our small eigenvalues. So it kind of measures how much change we're making at the lower part of the spectrum. And this is a variation of this method is used at ECMWF. So that's why we're looking at these two methods. Theoretically, what happens to the standard deviations? Well, we notice we have a much less nice phrasing of the standard deviations. So we have our updated standard deviations, square root of the old variances plus this term. So VR is the eigenvectors of our original covariance matrix, and gamma was this difference between the threshold and our updated eigenvalues. So this doesn't look very helpful or informative, but we can bound it in terms of things that we know. So we can say that the smallest it can be is the original standard deviation. So we're either going to increase or stay the same. And we can bound it above by an expression that has the original variances plus this constant term and then the square root of that. So both of these bounds, you can find examples where you get both cases. So as you might expect, we can't say anything theoretically about the correlations and how they change in general because we don't have such a nice expression for how our eigenvalues and how our standard deviations are changing. OK, so we've got two methods, two lots of theory. Can we say anything about how they compare to each other? Yes. So first of all, the most kind of obvious thing is both methods either increase or maintain the standard deviations. So that means that we're going to be kind of less certain about our observations than we were before. We can say more. So both cases, we could have a bound or an equality in terms of the original variances plus a constant term. And we can show that the constant term for the minimum eigenvalue method is strictly less than the constant term for the ridge regression method. So for the same target condition number, we're going to have smaller standard deviations for the minimum eigenvalue method than the ridge regression method. OK. Now we've got a case study looking at an example using diagnosed correlation covariance matrix from IASI. So this is a satellite-based instrument. It measures infrared radiation. And so the covariance matrix basically has different channels that measure different parts of the infrared spectrum. The reason we're looking at this matrix is because it's quite well studied, and it was the first matrix where correlated observation errors were kind of estimated. When it was used, the estimate you get out of the de Rosier et al. Diagnostic really ill-conditioned and causes convergence problems. And we're looking at a subset that has 137 channels, and it has a condition number of 27,000. So that's quite large. And because of this instrument, because it's an infrared instrument, it is affected by cloud. So this means that we're not just using the full matrix every time. Otherwise, we could invert it once and just store it. But what happens is kind of each time, there might be different channels that we can't use. We'd have to either have a big storage issue of storing lots of different inverses or invert it on the fly, which is expensive. Hence, with the interest in reconditioning. OK, so this is what the estimated correlation matrix looks like. And we can see this might be a good candidate for reconditioning because we have like some strong structure going on here, but we also have what looks like possibly lots of noise that maybe we want to eliminate. OK, so first of all, we're going to look at what happens to the standard deviations. So the black line is our original estimated standard deviations. The blue line is the minimum eigenvalue, and the red is the ridge regression. So the good first thing is that our theory is true in practice, which one would hope. So we have the ridge regression has a larger increase than the minimum eigenvalue to standard deviations. And one thing that kind of relates back to Alison's talk is that we see larger increases to the smaller standard deviations than we do to the larger. And this is because if you think about when we're taking we had the variance plus a constant. When we take a square root of that, that's going to have a larger impact on the smaller values. One other thing that's good to point out is, although we've got these changes, we're still keeping a lot of the structure from the original standard deviations. So we still capture these peaks and troughs here. So we still are preserving some of the information that we had originally. And this is for a target condition number of 100, which is much smaller than the original 27,703. Correlations. OK, so the color scheme on this requires a bit of explaining. So we proved theoretically that we're going to reduce the absolute value of correlations for the ridge regression method. So here, red on the scale means that we're reducing the absolute value of a correlation, and blue means we're increasing the absolute value. So the left panel shows the ridge regression method. So everything is red, which is good. And we can see that there are areas where quite a lot of the correlation is being removed. But there's also areas where these more noisy components seem to be being removed as well. Looking at the second panel for the minimum eigenvalue method, we can see that there is a lot of blue. So we're actually increasing the absolute value of some of the correlation entries. This looked like a lot, if we go back, a lot of the more kind of noisy, like negative, possibly more noisy areas is the same area here. But there is this one block at the top of structure, which is the absolute value is decreased by the ridge regression method, but increased by the minimum eigenvalue method. But if we look at the kind of red portions, they appear quite similar. We might ask how similar those are. If we look at the third panel, this shows the difference between the two methods. So red here is that the ridge regression makes larger changes, and blue is the minimum eigenvalue method makes larger changes. And we notice that most things are red. There's a small bit of blue around the diagonal, but it's mostly red. OK, so this kind of compares the two methods. So we can say more theoretically about the ridge regression method. And we know that it preserves the structure in the sense that we're only decreasing the correlations and increasing the standard deviations. However, the minimum eigenvalue method, we are making smaller changes, but we're not necessarily sure what those changes are doing. OK, so ongoing work. I actually have a poster, so I'm going to do a quick promo of that as well. This whole talk has been about how reconditioning is important because of the convergence of a system, which is good because if it doesn't converge, we can't use the information. However, by doing reconditioning, we're actually changing the problem that we're solving. So it's really important to make sure that the solutions of a reconditioned, when we're using reconditioning, are close to the solutions in the original problem. So we've done a case study studying what happens if you use reconditioned covariance matrices in the MetOffice 1D var system. And if you want to find out more, it's poster number 23. OK, so wrapping up, we've developed some theory about two methods of reconditioning and showing how they make changes to covariance matrices and what happens to the standard deviations and correlations. We've shown that the ridge regression method results in increases to the standard deviations that are larger than the minimum eigenvalue method. And we can say something theoretically about what it does to correlations, moving everything closer to 0, whereas the minimum eigenvalue method we've shown in practice does not do that. And we've shown that the correlation entries are changed by a larger amount for the ridge regression method than for the minimum eigenvalue method. So I would say these are just two methods of reconditioning. There are many more out there, and the kind of study of these was motivated by the fact they're being used in practice. I'm not saying that either of these is the best or the worst. But yeah, hopefully going forward, one thing that would be interesting is to have a slightly more rigorous method of choosing this target condition number. And that's kind of something I hope to be doing in the future. So thank you.